In this video, I'm going to be going through the 2014 HSC Engineering Studies paper. The first question is, which test is used to test workability of concrete? That is a slump test. So this is where you have the cone, you fill it up with concrete, you lift up the cone, you turn the cone upside down, you measure the difference. If you look at my picture, my Sam Rockwell testing super thread, that's where you'll find more information. Okay, so here we have couplings under load. What kind of shear is it? It's under, well, let's have a look. So this top half of the pin, it's being pulled to the right, and then this next section is being pulled to the left, right, left. So let's, if we look at, let's see how many change of direction. Right, left, 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 right, left, left, left. So there's 1, 2, 3 changes of direction. So that's triple shear. Neither of these questions, despite being part 1 and 2, were particularly well answered. Slump test, because I came from civil engineering, I actually conducted slump tests, not many, but a couple. This shear question, to me, this has always sort of been fairly intuitive, but I do know that students really struggle with this. So I think my students probably get the slump test because I labor that point when I talk about it. Whereas this, I just find the best way to think about it is we've got a sort of a tug of war here, and how many times is this thing changing direction? So effectively it's being cut at this location, and this location. So that's the best way I have to describe it, and it doesn't work for everyone, but it works for me. Okay, so we're going to move on, and I thought I had it. Yeah, there we go. Okay, engineers, there's a floor and a pylon. Okay, so how are we going to test if there's an error without testing? Okay, so we're not going to use, I mean, I don't know what a bend test is. That might be like a transverse beam test or something like that. Eddy current and dye penetration are both surface tests, so radiography is the answer. I'm going with B, and most people got that. Okay, which of the following is yaw? So roll is the aileron, pitch is the rudder, and yaw is the... No, sorry. Yaw is the rudder. I jumped ahead of myself for a second. Pitch is the elevator. So we have Ron Weasley in the car, and next to his friend Harry, who's been turned into a roll. Aileron means little wing. Elevator, we have Fat Amy from Pitch Perfect, Rebel Wilson, and she's in an elevator. And for yaw, we have the shark, yaws. You know, it's like Jaws, but you know, in some languages, J is pronounced like a Y, and it's a shark with udders. So that's how we get to that. So the answer is rudder, and yeah, 2/3 people got that. Okay, which one looks like quenched high carbon steel? Well, so which one is looks the most needle-like? And I'm going to say that of these, I think A looks the most like a circular martensite. Less than half people got that, but you know, this test was a long time ago, so who knows? People might be better at that now. I would say that this is probably mild steel, and this is probably high carbon steel. I'm not really sure what's going on here. That could, I guess that's probably like graphite flakes, and that might be cast iron. Okay, an engineer designed a warning system. Okay, so the statements are represented 1 if true, 0 if false. Which one represents a situation where the passengers are not seated even though the ramp is on board? So we're saying ramp is A. So the ramp is on board is 1. Passengers are not seated, and therefore we can't go. So it's going to be, I guess, D. Yep, most people got that. Okay, so this is a question about parallel resistance is the thing we're really testing here. And so parallel resistance, we've got 1/3 plus 1/6. The inverse of those numbers is the resistance in this circle. So we've got 1/3 plus 1/6. Take the inverse of that, and that is exactly what we have here. And then we're adding 2. So that's A. Again, less than half the people got that. So okay, so question 8. A conductor has 200 volt, 2000 volts. So what would you use to measure the resistance? So We can use a multimeter, which I think is I mean, multimeters can be used indirectly to calculate resistance, but megometers are the better things to directly calculate resistance. And yeah, they're called megas. I think I have in my signal testing, like in my notes in Google Classroom, where I have infrared, Wi-Fi, and signal testing all clumped together, and cell towers. I have a video on how to use a mega. Okay, so I mean, it's true to say that the multimeter just does what the ammeter and the voltmeter do anyway. So it's true that we could use, if we know the voltage, which we have here, we could use the ammeter to calculate the resistance. This is why the mega is the right answer. Okay, so we've got two pistons, 15 and 30 mil diameters. How far? That's the difficult thing about this question. How far will the out piston move? Okay, so in this case, the thing to think about is when we press down on the input piston, how much volume is being displaced? So the way that we can look at this is that we need to calculate volume is equal to area times height. And what we can look at is the areas are equal to, so with the diameter ratio is 1 to 2, which means our area ratio is 1 to 4. So because this is 4 times the area, it's going to move up 1/4 as much. So that means that if this moves 20, this is only going to move up 5. That would be my answer. Are we up to 9? Oh yeah, that's fine. Okay, yep. And not many people got the mega. I mean, that's a hard, I think it's not something we go into a lot of detail. I do include it in my notes because of this question. Okay, this is a question I really don't like. And when I was talking to my students about it, it's like, I said to them, I don't really understand what this question is trying to test. Is it trying to test, assess whether or not we have the skills to be a metal fabricator? Because that's a pretty esoteric skill for engineering studies students. And but I mean, that said, I think it's also, I would have got this question when I saw it on the in the paper, because we're given the inside diameter, inside radius, we're given the outside radius. So if this started out life as just a flat piece of metal that was then bent, and I mean, it says that it was folded. So what we're interested in is the average of those two, which it's taking the average of 20.5 and 12.5 is 16.5. So I mean, I'm not really sure what this question is here to assess, and it was answered. Only 1 in 6 kids got that right, and I mean, I sometimes mention that it's multiple choice. So if you got your puppy to press a button at random, your puppy would do better than the engineering students did on this question. So keep that in mind. I'm not sure what it was really intended to assess, and go from there. Okay, which of the following does not contain a semiconductor? I love this question. I use this sort of thing all the time. So diodes, rectifiers contain diodes, diodes are semiconductors, transistors are semiconductors, resistors do not contain semiconductors. And still only half the people got this. I mean, there's no questions here that, I mean, yeah, I guess the first 3 and 4 were answered well. Okay. So for this question, I had to do some working out. So what I said is I labeled this point as P, and I said some of the moments about P. I said, well, okay, so there is a force that presumably is acting at P, but we haven't been told about that. So I wrote that and multiplied by 0. We've got the tension of the cable. It's going anti-clockwise. And then I've broken this 100 into 86.6, the disco number, and 50. And I've just replaced this 100 with those two forces. Now, I think the thing that would people would get in trouble here is they forget to take the 50, and they forget that the 50 is going anti-clockwise. So we're so used to both forces being going the same way. Another way that you could approach this question is you could have found the perpendicular distance. So you could have said 100 times 0.866 times 150, which was the disco number. That would be the perpendicular distance here. It didn't even occur to me to do that when I was writing this question. That would have actually been faster, and that would have required a little bit less work. But here's where we are. Okay, so the next one we're going to look at is this pulley system. Now the trick of this pulley system is you need to know how to calculate the velocity ratio of pulleys. So it is the number of ropes attached to moving pulleys. There are 2 moving pulleys and there are 4 ropes attached at 1, 2, 3, and 4. So the mechanical advantage is calculated by load over effort. The load is 120 kilograms, which multiplied by gravity is 1,200. We're applying a load of 400, so we're getting an advantage of 3 times. And the velocity ratio is 4, we just observed that. Efficiency is 3 over 4, gives us a percentage of 75%. Okay, how were those questions answered? Not well. Either of those were answered well. The puppies were doing pretty well on question 12 and only slightly better for 13. Okay, this question here, 1 in 10 people, so I mean the puppies are just destroying this question here, which is crazy to me. But it isn't, I think it's an ambiguous question because it relies on a piece of information one way or the other. The thing is, it says, which of the following sectional front views? It doesn't say half-sectioned front views, right? So because it doesn't say half-section front view, we rule out D. But D would otherwise be perfect. The problem then is that we have A. A is also fine. The problem with A is if it's a valve is made out of 2 parts. And so it says an inlet valve. It doesn't say a component is made out of 2 parts. So the question is, which one are we going to go for? Because I'll just quickly explain. So why is B wrong? This line here is what makes B wrong. That if it's 2 parts, it looks like A. If it's not 2 parts, that line shouldn't be there. So if that line wasn't there, then B would be fine, but the line is there, so it's wrong. And then C is just totally wrong. So C is just a mess. C would be like maybe if a third of the thing was removed, and we just don't do that. If we took out 1/3. So the answer they want us to give is D, but I did say before, it doesn't say half sectional front view, so I can see that, you know, why students are would be confused. I think I've talked about this in another video recently, and when I spoke to my students, I said, look, when I have put this question in papers, I will either say which of the following half sectional front view, which represents a half sectional front view, or I say that the inlet is made of a single component, and that makes it clearer as well. Otherwise, I have also, in the past, when I just took a copy and pasted the question in my early days of teaching, I put this in as, I marked A and D both as correct. So that's what I think about that. Okay, so for question 15, the first thing I did is I looked at the forces here, and I said, okay, what is this beam going to bend like? And so I said, and this is something I learned at uni, you look at how is this beam going to bend? It's going to bend in this sort of shape. My bending moment diagram is going to be the exact opposite of that shape, right? So this one here, it's not going to be curvy, right? So this one here is curvy, whereas the same idea though, it's going to be the opposite shape. Now I can't know whether or not it's going to be where the maximums are going to be, but it gives me an idea, it helps me to understand what shape I'm going to produce. Now, the next thing to know is that when you do calculus, you know that the maximum and minimum points are where we cross the x-axis, right? So our maximums, we've got 2 values, our turning points, right? Our maximum or minimum are going to happen at either A or C. So straight away, our answer is about A or C. Now, to calculate, we have to actually figure out what's going on here. Now, I drew the bending moment diagram, and I think a good opportunity to talk about bending moment diagrams anyway. And so what I've said here is that here, the height of this square is 2, and the width is 4, so it's plus 8. It's above the line, so it's plus 8. So I go from 0 and I add 8. And then now the height of my my next box is minus 1 times 2. So that gives me minus 2. So I have 8 minus 2 equals 6. And then the next block is minus 4 high and 4 wide. So minus 4 times 4 equals minus 16. So I go from 6 minus 16 gives me minus 10. And then finally, my last block is plus 5 times 2 equals 10. So minus 10 plus 10 gets me back to 0. And if you don't get back to 0, then you're going to have a problem. So a bit of a Sound of Music reference for you there. Anyway, so if I did this question, I wouldn't have drawn the bending moment diagram. I drew it because I'm trying to explain it. I've looked at this question lots of times. I really like this question. And you can say, well, okay, know what the bending moment, the maximum minimum is either going to be the left-hand side or the right-hand side. And you can just say, well, 8 or 10, which one's bigger? It's worth also noting that in some circumstances, the plus 8 is very different to minus 10. So if we're talking about a concrete beam, the minus 10 represents the steel at the top, and the plus 8 represents the steel at the bottom of the, so it's relative to where this curve is, right? That's where we're putting steel in. The plus 8 means the steel that we need at the bottom is going to be based on 8 megapascals. And here we're going to need steel, we're going to need more steel at the top of this beam. Now that's not something we go into a lot of detail, but this is, again, I mean, I did civil engineering or even focusing on structural. So this is something I'm more familiar with, and this is what I did as like my actual job. But if it's a steel beam or a timber beam, it doesn't matter. We just take the bigger value, right? And in this circumstance, we don't have any other information, so we're just going to take the absolute value. So even though it's minus 10, it makes it a bit tricky, but the answer we still want is point C, which is... That wasn't answered too badly. 2/3 of people got that. Okay. So, on to C. Ceramics are good insulators because ionic bonds have no free electrons. Yep, that's mostly true. Or that's the most correct. Okay, so another calculation question. I will go back to my notes. Okay, so we have a 2-ton vehicle. So straight away I write mass equals 2,000 kilograms. If I'm pointing this out at this stage, if this is news to you, I've done something wrong, but it's worth saying a ton is 1,000 kilograms. You were expected to know that. So that is assumed knowledge in this course, that you know that a ton, spelled T-O-N-N-E, so it's a French ton or a metric ton. You could think of the double N's looking like an M. You could think about Napoleon introduced it, and Napoleon's got 2 N's. Lots of different ways to think about it, but ton is 1,000 kilograms. So a 2-ton vehicle is stationary. Oh, and straight away, when I write M, I then write mg. By doing that, I don't give myself an opportunity to make a mistake. Okay, it's on a slope and ignoring friction. So I really like this question. I've used this sort of question, maybe even this question specifically, in lots of my trials. It's Ke equals Pe. And so straight away, Ke is half mv squared. That's in the formula sheet, right? It's there. And Pe equals half mgh. The m's cancel out, so that's how they managed to get away with out telling you what the mass of... oh, they do tell us the mass, but yeah, we don't even need it. But you know what? I'm glad that I wrote 2,000 there anyway, even though I wasted a little bit of graphite on that. Still worthwhile. Okay, so then I've rewritten this equation by multiplying this side by 2, this side here by 2, and then taking the square root gives me... okay, first of all, in order to do that, I have to find the value of h. So if I know this slope is 20 meters, my h is going to be 20 sine 40. If you're struggling with the trigonometry, you need to let somebody know, because we're pretty close to HSC at this point. The other thing I would say is get a protractor out and draw it to scale. Then we can say V equals 2 times 9.8 or 10, I think they actually used to the set, times 12.85. That gives us exactly 256. The square root of 256 is 16. Okay, the next question is also a calculation question, so we'll keep that up. Yeah, actually, we'll keep the formula sheet for the moment. So it says, what is the velocity ratio of the mechanism? It doesn't ask for anything else. It just asks for the velocity ratio. And so velocity ratio is based on distances or measurements. It's something we can look at. It's we know that it's always going to be bigger than the mechanical advantage. Okay, so the velocity ratio is the distance traveled by the effort divided by the distance traveled by the load. Now, I'm sure if you look at my YouTube video where I go through this specific question, I talk about how many times does the big wheel turn relative to the small wheel. Trying out something new. A student this year said to me, why don't you just find the velocity ratio of the gear and then multiply that by the two distances, and the two diameters. And I'm like, you know what? I actually really like that. So that's what we're doing from now on. So the velocity ratio of the gear is driven over driver. Now I had a picture of John DeLorean from the movie Driven and him running over Ryan Gosling from the movie Drive, because he's the character called Driver. Or otherwise, if you don't like what my nephew calls silly Darth Vader, Adam Driver, you could think about these people being run over as just a mnemonic, but whatever works for you. Driven over driver. I also have nor, driven over driver, right? Because driven ends in an N, over driver ends in an R. Yep. So I'm just chucking out different things. Whatever mnemonic works for you, good luck. Anyway, the point is that the velocity ratio of that is 20 over 50. So, and then comparing the two diameters, they give us this as a diameter. I think the diameter symbol has disappeared because when I printed this out, I printed it out of Firefox, and Firefox didn't render some of the letters. It didn't have the cover page, but yeah, it didn't say the word engineering. It said Sengineering, which I thought was pretty funny. I showed my boss. I thought that was funny. Anyway, what is the answer? 0.19. B. Okay. Yeah, I just gotta say, like, all of these multiple choice, if you did badly, don't worry. I mean, looking at the entirety of the 20 questions, there are only 3 out of 20 questions that 2/3 of the cohort got right. So don't feel bad if you didn't do well in these multiple choices. That said, it was a long time ago, and I like to think that people, we know more than we did then. Okay, so aluminium copper can be strengthened by which process? If we're thinking about aluminium, we're looking at precipitation hardening. So which one of these best represents precipitation hardening? We're going to heat to a uniform structure, then quench, then slightly reheat, right? Whereas heating to a recrystallization temperature, then cooling to room temperature, well, I mean, okay, it's not quenching, and it's the uniform structure. We need an entire alpha phase. So, yeah, okay. That's the answer is C. And then 20 to finish off with. Now, this was, well, again, this is a question that puppies are doing better than humans. So what are we looking at? To start off with, what we have is, what do I want to drive home? Okay, the reason why people did badly in this question, and, I don't know if I got this one wrong, but I know I put it in papers and I didn't write, because I type in the word so it looks better. I didn't include the compressive strength. And so what ended up happening is students who had practiced past papers did it one way, other people did it the other way. And so let's just start with, it says, what is the maximum compressive strength, right? And so, or stress. So that's really what we need to focus on. So first of all, this beam is going to bend in this smiley kind of fashion, right? Now that means that we're going to have compression on top and tension on the bottom. Why is that? Well, we can see that this smile here is smaller. It's got a smaller x distance than this on the bottom, which has a wider, right? So this top is being squashed and the bottom is being stretched. And, if you're looking at that folded bracket, the neutral axis is the original length. Anyway, so what's going on here? Well, what's that saying is, if we looked at for every part of this beam, because it's a T shape, it's not a rectangular shape, it's not a symmetrical shape, there's going to be different amounts of stress in this beam relative to everything. So what's going to happen is, it's going to be that the area of the stress has to be the same on top and bottom, right? And in order to do that, because this is so much wider, we're going to have a lot, but it's not as deep. We're going to have a big area of compression in this area, right? You get a big zone of big zone of stress in this area that's wider, and then for the rest of the T, it's going to be the same gradient. And it needs to be that this part here equals that part here. Now, I will tell you, I was in second year uni before I understood this, so if you don't understand that, don't worry. The point is that we find the neutral axis, and the neutral axis, because there's more stuff at the top than there is in the bottom, the neutral axis is not in the center, it's a little bit closer to the top. Now, we have two values. Okay, so the next thing I'm going to move on to is, when we're finding bending stress, we use the formula mi over I. Now, mi is actually moment times the distance from the neutral axis to the extreme fiber divided by the second moment of area. Now, again, I was probably in second year uni before I really understood what distance from the neutral axis to the extreme fiber meant. It's not a really catchy name, right? If I maybe had a band, I might call it the distance from the neutral axis to the extreme fiber. That'd be a pretty catchy band name. Anyway, what is the distance from the neutral axis to the extreme fiber? Okay, well, we know what the neutral axis is, and we know what distances are, but we have this concept of the extreme fiber, right? So the idea is that these atoms, right, they are under more compression. They're under the most compression in this beam. And these atoms are under the most tension in this beam. And this stuff here is under less and less and less and less until it's at nothing, right? There's no stress at this point, and then it starts adding compression. Now, normally, when we find the bending stress, we want to find the critical bending stress, and that's why I have a video somewhere where I say big Y, and I'm doing like a Y shape. The problem with smartphones. But anyway, big Y. If in doubt, use the big Y. Right? We've got two Y values. We've got Y for compression and Y for tension. And these are not the same. The Y for compression is 96 and the Y for tension is 154. Now, normally the critical one would be the big one. But in this case, they have asked us to find compressive strengths. So the thing is, some people look at this and they're like, I don't understand how I could do this. Compressive stress is an axial stress. And yes, normally we're talking about the compression that acts along the axis of the beam. But when you bend, you actually create tension and compression. Someone who wrote this paper really wanted to be smart, and they wanted to show that they went to uni and that they knew things, and they wanted to see whether or not students understood that there's a difference between the distance to the compressive strength, the compressive fiber, and the tensile fiber. So we're using this distance here. This is the distance from the neutral axis to the extreme compressive fiber. So we've got that value. The next thing we need to do is we need to find out what Y is. What M is, what the maximum bending moment is. Now, because it's a simple beam with a single point load, symmetrically loaded, I can use M equals P ln 4. Right, you can use that, but I only say only smart kids should use that because this is like the 3-force method. It's a power tool that you don't need. It's the egg machine. That yes, it makes perfect eggs, and if you eat a lot of eggs, it's going to be a valuable addition to your home. But for most people who don't eat boiled eggs every day, they just can boil their eggs in a pot, and you know what, their life is going to be 90% as good as most people. So by all means, use P ln 4. It's a great test, but instead what we're going to do is we're just going to draw a little shear force diagram and a bending moment diagram, and we talked about how to do that just above. So, I mean, if you don't know how to do this, check out my videos. I have extensive videos where I talk about bending. I like to think that, I'm the engineering teacher who cares, or in the top 2 or 3 who really care about bending. So, okay, that's how we calculate the bending moment. Now, we notice we get an answer of 12 kilonewton meters. Now, there is 1,000 kilonewtons to 1,000 newtons to a kilonewton and 1,000 millimeters to a meter. Because we've got this is where it comes together, right? We have our second moment of area, also known as moment of inertia. That's why it's letter I. The second moment of area about the x axis, don't worry, that won't make sense until you're at uni. The second moment of area, which is written as I, is written as 102 times 10 to the 6 millimeters to the power of 4. Now, 4D chess aside, what does millimeters 4 mean? Doesn't matter, you don't need to worry about it. And again, one of those things I didn't understand until second year uni. but they've given us millimeters, and we do not want to convert this 4D chest thing, right? We're just going to leave it. So that brings our grease unit song. We go together like megapascals and millimeters squared. So we're going to convert everything to millimeters squared, and our answer is going to be megapascals. So we're going to take this 12 kilonewton meters and we're going to convert it to 12 times 10 to the 6 newton millimeters. And so we've got 12 times 10 to the 6 newton millimeters times 96 divided by 102 times 10 to the 6. The 10 to the 6's cross out, and that pretty much always happens, right? If you look at the section guide, so if we look up, I always use the big beam. This is kind of the biggest beam that you buy, and in Australia, this is a place that these people sell steel. And when we look at their material properties, do they have material properties? No. I mean, I normally use this one, but that one's okay. Jeez, $6,000 a meter. Okay, so this is this is the first hit when you click on it. I just wanted to see if there was an Australian site. Oh, here we go. One Steel. So I have the One Steel book at school. It's the red book. I use this all the time. And when we're looking at I values, does it have I values? We've got Z. Oh, here we go. So we can see all of our I values are given as 10 to the 6. I'm just going to zoom in. All of our I values is given as 10 to the 6 millimeters to the power of 4. This is why I think Copeland is wrong, and that Copeland should be using millimeters 4 in his examples rather than meters to the power of 4. That said, in the recent HSC, they did give us, like the 2020 or something like that, they did give us the second moment of area to meters to the power of 4. I did not like that. I don't think that we should be doing that, because it's just not standard practice and it makes life more difficult. But we can see that these are sorts of values. So, I mean, based on this, we could look up, I mean, you can actually get T sections. If we go to the One Steel page, we could actually look up the T section, find the exact T section that we're looking at here. We don't care, right? We're just going to move on with our lives and say that let's go with, we're going to need that in a second as well, so that's good. Okay, so when we type in those numbers, we get about 120 divided by 100 gives us 11.3. So moving on. So we're on to, is this the right paper? 2014. Yeah. See how there's the 0 is not printed. Oh, it is. But I took out some questions because I didn't have any scanning. There wasn't anything interesting. Okay, so I've talked about this recently when I was talking about a trial, because I do include this in papers. I'm just going to, for the sake of symmetry. Yeah, that looks better. Okay. Contrast how these ferries are used to provide public transport. Oh, like, the thing is, I look at these questions and I put my head in my hands like Picard. I'm like, what do you mean? But what you got to remind yourself is, it's question A. Nobody else understands what this question means either. You just got to write down something. So you got to look at them and think, okay, there's two ferries. Contrast. Now, I haven't looked up the HSC keyword, but let's have a quick look at that one. Contrast. Show how things are different or opposite. Okay, so how are these things different? So we can say that the contrast how these are used to provide transport. Okay, I would say that the single hull ferry is a single hull. So we got show a large single hull and a smaller twin hull ferry. Okay, so I would say that the larger ferry carries more people, and it has the single hull is submerged deeper into the water, whereas the twin hull ferry is less submerged, and because it's smaller, it's better suited for shorter trips with lower passenger content. Now, is that a great answer? It's probably not, but we've got to remember, it's question A. The markers are looking to give marks. You've got to take an attempt at these things. There are a number of papers where I've looked at these questions and I've just groaned, and I thought, you know what, I'm going to write down something. And when I looked at what marks are given from HSC markers, I can tell you that as long as you've written down something, and as long as you've compared them, as long as you've said that the single hull ferry is big and it's carrying more people, you're probably going to get 2 marks, just straight up. So let's have a look at what the HSC said. They said single hull ferry is much larger. Yep, we said it's deeper in the water. It's carrying more people between 2 wharves. The twin ferry is shallower. Less wash. I like that. It's more maneuverable. It can pass under bridges. Now, don't read this second paragraph and think that you need to write all 3 of these things in order to get that 3rd mark, right? If you wrote any one of those things, if you said less wash, great, good knowledge of boats. If you said it's probably more maneuverable, great, good knowledge of boats. If you said it's probably able to pass under bridges, great, good work. You looked at the picture and you applied some thoughts. You could also talk about speed and stability of catamarans, right? Now, we don't explicitly teach boats as part of the course, right? Most teachers, when we talk about personal public transport, we tend to focus on bikes and on trains. So keep in mind that when we see a weird question, when we see a question that looks difficult, remember that everyone is struggling with this, and that, you know what, most people, when they take a shot at it, they still get 2.5 marks on average. So the markers are going to try and give you marks, but they can't give you nothing. So they can't mark nothing. If you don't give the markers anything, they can't give you anything. Okay, moving on. How does a hydrofoil operate? So this is a question I like to use because there have been hydrofoils on more than once. I think there, about 5 years later, there was a hydrofoil. We're probably not due for a hydrofoil yet, but there's some interesting questions. So we can say that the hydrofoil operates the same way to an aerofoil. If you wanted to add that, I don't think you'd get any marks for that. What we'd say is the fluid, right? Air and water are both fluids, but in this case we could say the water passes over the top of the hydrofoil faster than the water below. This creates an area of low pressure compared to the water below. The difference in this high and low pressure generates lift. And then for me, when I was marking this, I put this in my trial this year. I said to my students, for the 3rd mark, you need to talk about something else for that 3rd mark. So you needed to say, this is due to Bernoulli's principle. Or you need to say, this reduces the drag and makes the boat more efficient, right? That's what I'm looking for that 3rd mark. So let's have a look what they said. Lift produced hydrofoil, reducing drag, right? So they've said reducing drag. That was one of my real points of difference when I did my trial, but I deliberately put this question in my Google Classroom so that my class was ready for it. Okay, so outline factors that an engineer needs to consider when designing a ferry wharf. Again, this is one of those ones where these sorts of management questions, so there's been ones on like, where would you put a telecommunications tower? It's not a bad question, it's just, if you're not ready for it, and this is where doing practice papers helps you to prepare, I can see where people look at this and they think, I just don't know, this wasn't something I studied for. So what you got to think about is, okay, you're going to build a wharf. What are the considerations? What are you going to think? You don't put a wharf in the middle of nowhere, you put a wharf near something. So you think about the needs of your users. You think about where the traffic generators are. You think about the safety. You think about the depth of the water to make sure that the boat's not going to get, when it comes up on a sandbank, run ashore, run aground, right? So straight away, I would say I want to make sure that it's somewhere safe. I want to make sure that it's somewhere useful, and I want to make sure that it's somewhere functional, right? I think if you had these sorts of questions, 3 marks. Outline. Outline is one of the key words. It means sketch out in general terms. What else? Sketch out in general terms. I don't like outline. I think outline is the most vague one. And indicate the main features of. right? What does that even mean? Well, for me, it just means it's 3 marks, write 3 sentences. It means 2 good things or 3, three general ideas, or 2 answers explained well. That's been my experience. So, outline factors that an engineer needs to consider when designing a ferry wharf. I think that you can always go with safety, functionality, and usefulness, right? They're the 3 things that I would look at. And if you think about whenever you see one of these questions, safety, functionality, and usefulness, that's probably a good starting point. Okay, same applies if you're doing the question about the telecommunications tower. Modern wharves, okay, it says we can't talk about protective coatings. Man, I love protective coatings. So things like galvanizing or painting, or even chrome or nickel plating, something like that. Now, stainless steel is not a protective coating. So you could describe stainless steel, and that's not an unreasonable thing to say that the... so we say often use steel, so we can say stainless steel, I think is reasonable. I think that's at least open enough to interpretation. You can't say use aluminium, because it said specifically talk about how steel can be protected. Now, short of saying using non-corrosive alloys, the answers that really we can use are ICCP. So I always think of the clowns, the insane clown posse, but that is cathodic protection, or impregnated current cathodic protection. I just write ICCP because I can't remember what it stands for. Anyway, but so the insane clown posse, and that is where we apply a current, and the current, when we lose electrons due to corrosion, we provide replacement electrons preventing the corrosion, right? Now, is this suitable? We tend to use ICCP on structures like pipelines. Is that suitable for a wharf? Well, it's a big structure. I'm not a marine engineer, so I can't tell you. The other option is we can put on big blocks of sacrificial anode. So a sacrificial anode is where we put an anodic block. Usually we use zinc because it's cheap. And when the corrosion occurs, the sacrificial anode corrodes, and it rather than the structure that we need to protect. When it corrodes away and it needs to be replaced, we can just buy a new sacrificial anode and replace it. Let's have a look at what the answer said, because I haven't actually looked at the answer for this, so I'm interested to see what they say. Okay, so I hadn't looked at the Ferry Master's knowledge. Visual aesthetics, yeah, that's not a bad one. Maintenance, building access, all 3 of those are great additional things. Customers, yeah, so usefulness, accessibility, appropriate materials, discouraging vandalism, great answers. Okay. So the best answer they like is ICCP. So impressed, I think I said impregnated. Anyway, impressed current cathodic protection. It's used on larger structures where a sacrificial anode cannot supply enough current to provide protection. Also, you could say cathodic protection, a sacrificial anode. Yep, so they would have also marked that as correct. They don't specify here stainless steel. I don't know. I make the argument I think that stainless steel should be acceptable, but yeah. Okay, so let's move on. The diagram shows a roof truss supported on end. Determine the magnitude of the reaction of pin A. 3 marks. I think it's pretty reasonable, 3 marks. Reactions are going to be in your HSC, right? They're just going to be. They've been in every HSC since, for as long as they've had engineering studies, and even back in the days of engineering science. I'm pretty sure that there has never been a test that did not ask you to calculate reactions. So if you don't know how to do reactions at this point, I'm not going to say panic, but this is the thing you need to prioritize. You need to tell your teacher right now. Okay, because this is going to be in the test. Okay, so at this point, I mean, I've done this question specifically on YouTube where I've worked it out, and I've done the calculation. I have my working out here, so I'll just bring that in so that you can see it. There's my working out. I was tempted to say, hey, it asked me to find reaction A. Can I just find reaction A by taking moments about E? And then I realized, oh, I could, but then I would have to find like this weird perpendicular distance, and I don't want to do that. So I'm like, hey, look, they've given us this perpendicular distance to A, and this is the way to do it, right? We could theoretically do it the other way. The problem is we don't know the angle of A, and because we don't know the angle of A, we'd have to break up in vertical and horizontal components anyway. So, yeah, this is how we get the answer. Let's just check that is how they did it. They take some of the moments about A, find a reaction E. Okay, done. So they did the same way as me. Okay, the next one is the truss. I like my working out for the truss better, so we're going to look at my working out for the truss. So, that actually works out really well. So, this is what we're going to do. First of all, we need to cut the truss somewhere, right? And obviously there's ridiculous ways we could cut the truss, like we could cut the truss horizontally, right, and cut through 1, 2, 3, 4, 5 members. That would be ridiculous, right? We need to find somewhere that cuts through the target member. So BC is our target member. We need to find somewhere that cuts through BC in such a way that it only cuts through BC and 2 other members maximum, right? Anything more than 2 unknowns, we're going to have a problem. I've drawn up a little sketch. I will tell you that when I've drawn up little sketches, the problem that I have is I forget to include forces, external forces. So don't do that, right? Make an effort of saying, hey, Pun's told me that he forgets to include the external forces. I better check again and check the external forces. All right, one more time, check the external forces. Don't forget to draw the external forces. So this is our loading condition. And what we're going to do is we're going to take, so we've got 3 members, BC, BF, and AF. Now, BC is our target, and that means BF and AF are our destructors. Now, the first question you should ask is, do they share a letter? Do they share a letter? It turns out they do. They both have the letter F in them. If they have the letter F in them, that means they're going to meet up at point F. If they meet up at point F, we use the meetup method. If we use the meetup method, we use moments. There's an alliteration there, if that wasn't obvious. Meetup, moments, right? So where do they meet up? They meet up at point F. We're going to take moments about point F. By doing so, we're going to take BF multiplied by 0 and AF multiplied by 0, and we just ignore them. That's the beauty of moments. That's the reason why we use moments, is we can just ignore them. They just disappear, right? They multiply by 0. Anything multiplied by 0 is 0, and they disappear. I don't need to write that BF times 0 and AF times 0. By doing that, it actually takes up a lot of space, and I always end up running out of space on my whiteboard. And when I wrote this, I actually had to rub it out and move it over a little bit so that, because I started there. But I just put it in there because I want you to know that those 2 members, they do still exist. They still have forces, but because we're multiplying by 0, we can ignore them. Okay, so then I have 3 other forces. I have my reaction at A, I have my external force at B, and then I have BC, which we're finding. Okay, so our force at A is half of 15 away. Our force, and it's going clockwise around F. Our force at B is a quarter of 15 away, and it's going anti-clockwise, so it's minus. Now, for BC, we don't know if it's in clockwise or anti-clockwise, but we assume everything is pulling out, and if we assume it's pulling out, it's going to be tense, right? So it's in tension, and the distance, so because it's in tension, before we worry about the distance, if it's pulling out, it means it's going to be going clockwise, and that means positive. So I've written here, assume tension, therefore clockwise. I've written that above just as a little reminder. You don't need to write that, but I do because I want people to know what's going on. Okay, so BC is, how far away is BC? Well, you can see we need to find the perpendicular distance, and I've just shown that perpendicular distance as D. And they've drawn a little diagram here to help us. It's like, oh, it's just trigonometry, right? We know the hypotenuse, so this side is going to be, well, it's a 30-60 triangle, and so when it's a 30-60 triangle, we know that if the big side is 100, the little side is 50% of that. But you could also use your trigonometry and say 7.5 sine 30. One way or another, we're going to get an answer of 3.5 is the answer. So when we put all that stuff in the calculator, we get 15. It's negative, therefore our assumption is no good. Therefore it's in compression, so it's 15 compression. DC, it's not DC, it's DF. I've written DC, but anyway. It is, again, I always say I did this in an hour, so, be kind. I did skip some questions, so don't be too kind. But anyway, this thing here, I always think of it as a straight line angle. Whenever we have a straight line angle, if we have three members that meet together at a force, no external forces, it's going to be the one that is the odd one out is going to be a zero force member by observation. The other thing that is zero force member is corners. If you're not sure, go and check out my notes. I have some notes in Google Classroom about zero force members. Okay, we can go back to our viewing. Okay, so the next thing we have is a question. Now, I had more than one student in the last month or so say to me, I didn't know what to do with this question. And I said, see how there was a force? See how there was a stress? See how they asked us to calculate an area or a diameter, right? Stress equals force over area, right? So where is that on the question sheet? That is here. Stress equals force over area. This is the second most important thing you need to know in my subject to not embarrass me. The other thing being concrete is made of cement and aggregates. Yeah, like we kind of expect you to know that. Determine the diameter. Look, I think it's pretty simple, but I'll just quickly show you my notes. The first thing we need to know is factor of safety is yield stress over working stress. I can see that my stress symbols there don't look particularly good, so I should probably be more mindful of that. So my stress that we're working with is 170, right? So we're taking the 272 and we're converting it to 170. Then we're saying stress equals force over area, rewriting that as area equals force times stress. So then we're going to calculate the area we need. It's 29 times 170 equals 170.6. And then I've said area equals pi d squared on 4. Now, the number of times I must have said in my life, if you're planning on going into engineering anyway, just get used to using it. I remember my teachers said it and I didn't believe them, but anyway, there's only so many times I can say this. Anyway, so also it's probably worthwhile to just not even memorize this formula. The diameter equals the square root of 4a over pi. It's not very catchy. Root 4a on pi. I can't. Not very catchy. But the more you write this out, the more you will recognize it when you see it in an exam. It's like, I know that looks familiar. Okay, I don't need to stress on it. I've probably got the right working out. And because we need to use these things, and if you're using pi r squared, it's just, it gets clunky and you got a good chance of having bad times. So, just quickly to point out before I move on, 21C. This was the only question in 21 that was answered well. Everything else was answered badly. And by the time we're getting to the truss, that was answered really badly. And, only like puppies are doing better than that. Oh, okay, no, they're not. That's not true. Sorry, puppy. It's not multiple choice anymore. Anyway, but the point is, it wasn't answered very well. So, this here, yeah. How's this question answered? 22.3. Yeah, still we're only talking like half the cohort, and still not much better. Okay, I can see why people might freak out about this question, and they say, okay, what are they asking? What kind of grains? I don't know. What kind of grains are they? Well, these are equiax grains, which means that they're roughly equal in all directions, right? They're not spherical, which would be exactly equal in all directions. They're just on average equal in all directions. And these are elongated grains. I can appreciate if you didn't know what they were asking for, I can see why people are, I just don't know what to write here. And then you have to know that this one is hot rolling and this is cold rolling. And I can see that people get this wrong, right? It's in Copeland's textbook. I include it in my notes as well. But the reason we're going to know this is because work hardening, cold working, produces elongated grains, right? So that's what we've got here. Okay, so which one are we going to talk about? You can talk about hot or cold rolling. What did I say? Okay, elongated. Okay, so we're cubing it. So we're saying explain, and I didn't even need to write anything because explain is how or why. How the change in grain structure has affected two, and I've written a box for that. Different mechanical. So I'm underlining that to stress that it's mechanical properties. You can't talk about density or, actually, as a matter of fact, what is a non-mechanical property? Hot rolling provides. It's not cold rolling provides dimensional accuracy, whereas hot rolling leaves a bad finish. Right, it has a scaled finish, and if it didn't say mechanical properties, I would have written that. Unfortunately, because it wrote mechanical properties, it kind of boxed me into a corner. I'm like, oh, okay, I'm going to have to say something else. So I just thought that was interesting. I'd be interested to see as a marker, if you wrote surface finish, I would love to give you marks, and I would do everything I can in the discussion with the other markers to say, look, this student's showing knowledge. Yes, I know it says mechanical properties, but, this is still, couldn't you argue it? I would really try hard to advocate for students, but I would expect that at the end of the day, the senior marker is going to say, look, unfortunately it says mechanical, we have to mark mechanical. So there you go. Okay, so we're going to say cold rolling. What is cold rolling? It results in greater tensile strength and reduced ductility because the density of dislocations increases. The idea is that when we have elongated grains, it's more difficult to move dislocations between grains, and the term they use for that is dislocation density. So that is the answer we're going with.
What would you say for hot rolling?
It would be exactly the opposite. If you wrote hot rolling, you would say that hot rolling has reduced strength, it has reduced tensile strength, but it has greater toughness. Why? Because it has equiax grains. I don't like that. I feel as though it's a little bit circular, but it has reduced dislocation density. So here they said hot rolling, they said equiax grains, which result in they really shouldn't have had an explain, because I think this is too hard for explain. They're asking for two properties. I think they would have been better off just to describe the effect. Yeah, because they're effectively asking how this process. I would say I personally would be okay with saying identify two properties. Anyway, it is what it is. We're moving on. Okay, so this I've got a nail, and you do see these questions. So if we write corrosion bent nail, okay, so the thing is, you look at this and you think, oh, but isn't that rusting? What's going on here? But so the rusting is not the red area. I know it looks like that, but the rusting is not the red area. The rusting is this bulge, right? And so this here, if we look at this one, it says the rusting is blue. Well, I used a different search term when I looked this up previously. Yeah, we can see sort of the blue area there. But anyway, I don't know what the indicator is. I guess it's some sort of universal indicator or something, but I don't know what the indicator is. I didn't do this particular test when I was doing chemistry at uni, or if I did, I wasn't paying attention. Anyway, the point is that there's a variation of this picture somewhere that says that the blue areas are where corrosion is occurring. So I've written here as a little note to myself to say that we have Rad Cat and Angry Ox. Why is the Rad Cat angry? Sorry, why is the Angry Ox angry? Because he's stressed. Why is the Rad Cat, he's rad because he's low stress, right? Why is he angry? Because he's got poor oxygen. Cathode has high oxygen. Which one rusts? The cheap metal or the expensive metal? The cheap metal rusts. Now that's not entirely true, but these are mnemonics and they're to help you. So in this particular case, what have we got? The nail has been bent. And because the nail has been bent, this area where it's been bent is under stress. This area here where it's been forged is stressed, right? So these 3 points here are the areas where it's going to be stressed. If you point to any one of these 3 areas, I think you would have got the answer right. So it's one answer for pointing to the anode and the other one for writing stress cell. So if we go to Corrodor, are we going to go to notes? Yeah, let's go to notes. And we're back. So here we've got our sacrificial anodes. Here we've got, do I have the cathodic protection? So ICCP is this. I've got my Rad Cat, right? And I've got my Angry Ox. I think it's always easy to think so. It's like a country music song. What happens if you play country music song backwards? You get your car back, your wife back, your job back. Why is he angry? Because he's stressed. He's got bad quality of air, and he's cheap metals, right? He's living out of cast iron, corrugated iron shack. Okay, so here I've got Corrodor, and there are 3 different kinds of attack. There's galvanic corrosion, where we have 2 dissimilar metals in contact. We have concentration cells, which are to do with oxygen content, right? So where we have like a scratch in paint. And we have stress cells. So this is like why welding is a problem, right? When we weld, we create areas of higher stress, and so we have to worry about stress cells. So, so if we're talking about concentration cells, they look like this. So the area of low oxygen rusts, not the area of high oxygen. But for stress cells, we're using the nail as a good example. But I think there's even somewhere where there's a question where it's like, do not weld, or here we go. A partially corroded welded joint is shown. What kind of corrosion? Truss corrosion, because welding. So it's from 2012 trial. Okay, moving on. Oh, development. Okay, so. I might at some other point record a video. I might record it with a compass. I might record it on AutoCAD. But for the moment, we're just going to look at my solution, and I'll try and talk through it. The first thing I did is I looked at, okay, what they want us to do is they want us to do a half development. So I don't think they'd use that terminology 7 years on. I think that they would say, designer, like they would be more explicit. But what we're going is from 1A to 4D, and what I did is the first thing I looked at is I just looked at which ones are these are true lengths. So I said, okay, 1A, it's a dot in this view, so it's a true length here. And then I said, what else is a true length? I said AB is a dot in this view, so it's a true length, and 1-2 is a true length. I can see that it's a dot here, so I can measure straight off. 2-3 is a true length. BC is a true length. CD is a true length, and 3-4 is a true length. So what are my non-true lengths? Well, it's 2B, 3C, D4, and the 2 triangulations we're going to need. So 2C and 4C are the 2 triangulations I've done. So what I've done is, this question is actually relatively easy. We can see that we have, because everything's parallel, right? I like to call this the plan, and this the elevation. The height in my elevations is the same for all of these. So what we're trying to do is we're going to find the hypotenuse, right? And we're going to say, well, clearly, I'll just quickly say here. Okay, so here we have, let's start here with 4D, right? 4D is this length here, and it's this length here. They can't both be right. They're clearly different distances. But because 4D is, we can look at this drawing and say 4D is not moving away from the camera. Point 4 and point D are both the same distance away from my eyeballs. that means that we can say, well, in this view, because they're the same distance away from my eyeballs, that it's a true length, right? We can just measure straight off. 3C, on the other hand, right, it also occupies this same point here, right? And 3C, it clearly can't be the same length as 4D because it's a diagonal, and a diagonal has to be bigger, right? So it can't be the same length. So what we have here is we have the top view, or the elevation distance, right? And we have the difference in the plan, which we call difference in elevation height. We have a word for that. But for this distance in plan, right, this plan distance, what I've done is I've taken that plan distance with a compass, and I've just measured from here. I just draw a line, and I said from here to here is that height distance. And then I get the hypotenuse. And the hypotenuse is the true length, right? So that's what I did. Now 4D and 3C are very, very close together. They're different, right? But you know, we can see that they're I took 4D, but 4D was actually a true length. Anyway, nevertheless, I don't know why I wrote 4D, because 4D is not a true length. 4D should be a true length. Yeah. Anyway, moving on. Normally I like to draw a little arrow to point down, but anyway. So once I've got these distances, let's see how I start. Now I'm going to show you a couple of tricks as well. The first thing is I take 1A, which is a true length, right? Easy. Then I say, you know what? I can look at this and I can say, that looks to me like it's 90 degrees, right? And it is, right? Because it's parallel, top and bottom, it's 90 degrees. So I can just draw out the true lengths of 1, 2, and AB, and I get that first shape for free, right? Pretty nice, right? Pretty easy to get that shape for free. Then the next thing I'm going to do is I'm going to find, let's start by finding C. So what I find is I take 2C off my drawing here. I find this distance, this diagonal, the hypotenuse of 2C, and I mark that out with a compass, and I get 2C. I measure from 2, and I use my compass, and I get 2C, and I know 2C is somewhere there. Then I go do the same thing with BC. Now BC is a true length already, so I just measure straight off, and I get my compass, and I set that to this length, and I just mark out, and I write out these little lines to explain what's going on. I know that C, if I know 2C is here and BC is here, well then C has to exist at this location. So the next thing I'm going to do is I'm going to find 3. Now to find 3, I already know what 2, 3 is. I know what the distance of 2, 3 is. So I draw this line. I say, well, 2, 3 is going to exist somewhere there, right? It's a true length, and I just say it's somewhere there. And then I have to find 3C. To find 3C, I set my compass to the true length of 3C, right? This diagonal here. I set that value, and I measure from C, and that's how I triangulate that location. Now, if I was lazy, I could just find BC and say, you know what, 3C is probably going to be parallel, because I look at it and it looks like it's parallel, right? And then I look at this other one, I'm like, you know what, that looks like it's parallel too, right? And I've just pointed out here that where we can see that these things, where they should be parallel to each other, right? So this thing here I think is also going to be 90 degrees, right? Because this seam is the same as the other one. It's going to be a 90 degree seam. So I didn't look at that. I mean, they look like they're about 90 degrees. So I am not suggesting you use that method, right? Because these methods, all of these tricks I said, they can get you in trouble. But what I'm looking at is if you don't know how to do development, so you start freaking out, these are things that can help as sanity checks to say, does this look right? And they can also help you to get some marks. So, I mean, what are we looking at? This is 4 marks. You can't afford to not get anything. You're going to get 2 marks just for doing this, right? 2 marks just... These days, I don't think they would have included this one. I think they would have just asked you to do 2 pieces. You're going to get 2 marks just for doing this, if not more, right? I think that doing these angles here will get you probably 1 mark. This will get you another... this length here will get you 1 mark. I've never marked a true length question, so I can't say definitively, but I think that they're probably going to be pretty generous with marks, and I think that you could be out by a fair amount and still be right. The big thing I'll finish on is if we're looking at something like 3C, right? Now I can see 3C in this view, and I can see 3C in that view. And let's say I know that it's not a true length. I've just determined it's not a true length, and I forget how to do this. Well, you know what? 3C is going to have to be longer than the two other sides because it's a hypotenuse. So if you're freaking out and you can't think of anything, you can set your compass and say, well, if I can see the bigger of the two sides is this one on the bottom, right, in plan, well, the true length, it's going to have to be a little bit bigger than that, right? And I'm not saying that you should deliberately write down, bad answers, but all the time we say, well, make a good guess. We don't tell people not to put, to fill in one of the circles in multiple choices. If you're unable to come up with how to determine the true length, it has to be bigger, right? 3C has to be bigger than both of these, right? And so if you just say, well, okay, if it's bigger than that, at least I've got somewhere to work with. Okay. Let's get back to the paper. Been quite a way up. Now, finding the center of mass. I don't like this question. I mean, this is the stuff that you do at uni, so it's something I can look at, and to me, it's it's again, what is this question for? Who is this question for? What syllabus dot point does this address? Effectively, what we can say is that this value here has to equal these two values, is how I look at it. So if I show you the answer, back here. Oh, I must have skipped something. Oh, sorry about that. In my excitement, I've skipped something. Oh. Yeah, I apologize. Outline the advantages of polymer roof guttering. Okay, doesn't need to be painted, right? You can include the color when you make the. So when you're making the plastic, you can include the color, so the color doesn't might not fade. Plastic doesn't corrode. Probably plastic is typically as heavy as aluminium for the same strength. So, I mean, for me, I can't go past corrosion. But if you said corrosion and it doesn't, it can be colored, that's already two. So we said that outline, we can write three poor things or two things well. So we'll expand on the corrosion, and we'll say that corrosion is an issue for gutters, especially if you have things like a screw. If you have a screw that gets left in your zinc aluminum gutter, that's going to be dissimilar metals, and that can cause problems. Yeah, it's not as big a problem. Flashing, you got to be really careful when you have guttering that you don't use lead flashing with aluminium gutters. What did they say? They said it's less likely to use corrosion and less likely to dent. Yeah, it's tougher, more flexible. Yeah. Okay. In the box below, name a polymer that's suitable for guttering. Describe the extrusion process for the polymer and draw a label diagram may be included. Okay, so once upon a time, my mentor told me that if you're talking about something like this where they're giving you, like, name a manufacturing process or name a thermosetting polymer, you just have to accept any possible one that is conceivably right. So if you wrote any polymer, I mean, I wouldn't accept low density polyethylene, but if you wrote polyethylene, I'm paying it. If you wrote polycarbonate, is it possible? It's a thermosetting polymer. Yeah, okay. ABS, I mean, realistically, it's going to be polyethylene, polypropylene, or realistically, it's going to be PVC. And why do I say PVC? Because we use that, we use PVC in guttering. If you look around, I mean, I can't see from where I'm sitting, but if I was to go outside, 5 meters, I would be able to see PVC guttering, out the side of my house. PVC downpipes are very commonly used. So we don't expect you to know that. It's just really that you need to name a thermosoftening polymer, and that you have a couple to choose from. I do stress polymers more than I think most other teachers do, because my first head teacher, she was really into polymers. And, I think, well, okay, I can use the knowledge that I have, like acrylic. Okay, well, can I imagine acrylic being used? Well, acrylic's maybe not, it's a little too brittle maybe for this application. But as long as you write something and as long as it's plausible, it's okay. Now, then it says, describe the extrusion process. Well, what we typically talk about, the main manufacturing process we talk about is injection molding. And the process is pretty similar. We have granules are fed into a hopper. The hopper for a thermosoftening polymer is tapered and heated. And when sufficient melt builds up at the nozzle, it's injected, it would be injected in an injection molder. When the melt is pushed through a die, which produces the extruded section. Okay, so you've said PVC, and yeah, granules are fed into a hopper, heated chamber, forced through a die of the shape required. That was almost exactly what I said. Okay, looks like I skipped this one. Explain how thrust is created by the airflow in the main operation of the two engines. You may add relevant information to the diagram to support your answer. Pause. Okay, I'm back. When I'm talking about jet engines, especially high bypass turbo engines, I have this video, A Leap into the Unknown, where we have anthropomorphic air molecules that go through an engine and have a great time. And as they slow it down, we can see the what happens with the molecules that go through the thrust. And then at the end, they're like trying to throw shade on the bypass air molecules and like, oh, we did all the work. And he's like, not quite, sunshine. Actually, the bypass air molecules did most of the work, right? And that's what they're trying to drive home here, is that see, this is not quite, sunshine. Anyway, and okay, so the purpose is not to see whether or not I would get the right answer. The purpose is to give you the best possible answer. So let's just read out what they wrote. Turbofan generates most of its thrust from the cowling or the bypass of the engine, which creates, yeah, like I said, most of the thrust. Whereas, okay, so what happens is the air that passes through, it turns a compressor. The compressor is connected to the fan, and that's what generates the thrust. In a turbojet, there's all the air is passed through. So we can talk about the four stages: suck, squeeze, bang, blow. We have a compressor where the air is compressed. So we have an intake. Then squeeze is where the compressor is compressed. We have bang, so we have a fuel injector where the ignition happens. We have the combustion, and then we have the thrust, which produces, in the case of a turbojet, 100% of the thrust. So that's the answer they're looking for there. Okay. Two control systems that are used to make modern cars safer. What did I say? I said, So it looks like I've gone past, here we go, I've gone past this now. I just keep missing things. Yeah, center of mass equals that. Yeah, look, I wouldn't include this because I don't think we explicitly teach this in the HSC. That said, this question has been there, so it means it means if it's in this HSC, it's in, it's by definition something you should be aware of. Yeah. Anyway, moving on. There's a pitot tube question, which I must have skipped, or I didn't write. So oh, it's worth pointing out, this is a 6-mark question. So there's going to be marks for, does it say label? It says add relevant information to the diagrams. So if you don't label, you're not going to get a mark, that's for sure. I would think about, so if I was doing this, I'd say, well, there's 4 marks, suck, squeeze, bang, blow. So that's 4 marks. Bypass, labeling and talking about the bypass is another mark. Talking about the bypass producing most of the thrust is the 6th mark for me. That's probably how I'd approach it. I can't find this pitot tube question though. Oh, here we go. Outline how a pitot tube operates. Okay, so the pitot tube allows air to pass, incoming air to enter a the pitot tube compares the pressure of incoming air to static air, and this is used to determine the flight speed, and it is also used to determine the altitude. That's my answer. I think it's pretty good for 2 marks. Okay, pitot tube compares dynamic pressure with static pressure, then determined, aircraft. They only talked about airspeed. It's only more recently that I've appreciated that the same pitot tube is actually connected to both the airspeed indicator and the altimeter. I didn't appreciate that until kind of recently, maybe 1 or 2 years ago, and that's why I have questions that are wrong in some of my tests. You know what? It's pretty hard to write tests, and I'm very appreciative of the people who write the HSC. Okay, describe the function of winglets on modern aircraft. So, the thing I would recommend is Real Engineering, winglets. Winglets, how do they work? And it's a pretty long video, and he just basically starts off by saying that, hey, they're pretty great innovation, and then if we cut to where do we have the vortices? Okay, so we can see we have big vortices without winglets. With winglets, we have smaller vortices. Also, we're going to generate more lift because less of the air is going to spill out over the edge of the plane effectively. That's my take on winglets. Describe the function of winglets. They reduce vortices and therefore reduce drag and increase lift. Boom, 2 marks. Let's have a look at the answers. Yeah, they don't talk about efficiency is good. They don't say the word vortices. I like my answer better, but this video is the video I'd recommend. I haven't seen this video, but you know what? We'll give it a watch later. I probably never watch it later, but you know, I do occasionally watch these things later, and that's how I get all my resources. Okay, so I think we're finally at the point where I haven't left anything behind. Sorry for jumping around. I appreciate that if you were trying to mark your homework, that would have been really annoying. Okay, so I wrote ABS detects braking to prevent spinning and reduces stopping distances, right? I talked about how, ABS is not very great for gravel and, not overcompensating, the video game that saved my life. Emergency braking uses radar, so I think it's like automated emergency braking, AEB. Anyway, I didn't write that though. I wrote emergency braking uses radar to measure the distance of the cars in front, and it stops. Measure the car in front and stops. Yeah, that's not great. I guess I got distracted while I was writing it. So just to explain that a little bit further, so I don't think it uses radar. I think it actually maybe uses LiDAR, but nevertheless, I don't think anyone's going to mark you down on that. Emergency braking detects the distance of the car in front. If it can see that the car is slowing down suddenly, it applies the brakes. Both of these technologies prevent crashes. I probably didn't need that last line. That's more if it would said explain, but I kind of felt as though I'd only written 2 things and I'd wasted a line up here. So also it says how it makes the car safer, and I'd underlined that. So I thought, you know what, better chuck in a safe, how it makes it safer. Okay. Now this is a hard question, and I got it wrong. So explain. Sorry, it says how is the electricity generated, stored, and then changed to a different voltage within the car. Okay, so how is it generated? We have something called an alternator. Now, you might not know that there's an alternator in cars. We don't explicitly teach that, and I don't explicitly teach that. I only know that what an alternator is because the first 2 cars I had both had an alternator die as soon as I bought them. Okay, so the alternator is a small generator in the car. All right, if you wrote small generator. Now, I said here it contains copper wiring which rotates. That is not true. The copper wiring does not rotate. The copper wiring is stationary. The magnet rotates. And movement plus magnets equals electricity. Anyway, you probably even write that and get a mark, actually. The alternator contains moving magnets. They produce electricity. Boom. I then spent 2 sentences doing that. Right? I could have tried to write a little bit shorter. Now, then I said this electricity reverses the flow of ions in the lead acid battery. Now, again, you probably should know about ion batteries. I think they'll talk about that in year 11. I think, as a matter of fact, it's in Copeland. We talk about dry cells and we talk about lithium-ion batteries. We don't talk specifically about lead acid batteries, which is what are in cars, I don't think. That's something that I'm sort of, my notes are getting better on. I'm sort of expanding my notes on those batteries. But the idea is it reverses a chemical process and the electricity is stored as chemical energy. And then the voltage is changed by transformers. Transformers are made by 2 inducers. If you want to learn more about inducers, I don't think that's within the scope of this course. Electroboom has a video on inducers. Right, I've linked that previously. I don't think that I've never seen it anywhere in Copeland's textbook, and I've read that book a lot of times, so I don't think you need to worry. Okay. Question 25. I just did technologies make cars safer. Okay, here we go. Outline the advantages of using optical fiber in telecommunications. The 3 that we typically talk about are bandwidth, security, and attenuation. So optical fiber, we get more bang for buck. We can send more internet for less money. They're more secure. So when we talk about security, it means it can't be hacked. So if we care about privacy, copper wire, you can listen in on copper wire. You can't listen in on optical fiber. And then lastly, the attenuation. So if you're using coax cable, you have to have repeater stations, whereas you need much fewer repeater stations for optical fiber. What do they say? Electricity, man, that's a very bad sample answer. It's only 2 lines and it's a 3-mark question. I don't really like either of those. Cruise control, the last year's paper, 2021, had a very similar question. Look at that one if you want a better answer. Question 2021. Okay, sometimes there's a benefit in going backwards. Okay. Bandwidth, I don't know why it's 2 words. It's faster, less attenuation, efficiency. Yeah, okay. So, I just looked at a trial paper that had this same thing. Actually gave a really good answer. Like the 2019 trial, independent trial, it had a really good answer. But it's funny, I read that just after I wrote this. I think my answer was pretty close. Okay, so how does GPS work? So the position of satellites is broadcast. So when I say that, I'm saying the satellites say, I'm here, I'm here, I'm here. It's like, it says, I am directly over Fiji. I'm directly 1 mile from Fiji. I'm 2 miles from, or they wouldn't say miles, they'd be in kilometers. But, for the sake of conversation, 4 miles from Fiji, 5 miles from Fiji, or whatever. And it says where it is relative to, some spatial coordinate. Right? So it says, now it also doesn't just broadcast where it is. It says, at 2 o'clock, I was 1 mile above Fiji, or 1 mile from west of Fiji, and at 1:01, I was 5 miles southwest of Fiji. That's a Twins reference for you. Anyway, big Arnie fan. Anyway, so it broadcasts the GPS broadcasts its position and the time it sends the broadcast. Right. The next thing it does is the device uses the GPS device. Right. It uses the distance of 3 satellites to determine where it is in space. Now, you have to use 4 because even though theoretically, and this picture here actually is pretty good, it demonstrates that if you have 3 circles, you can you could use, on a 2D plane, you can have 2 lines to find a location, right? So you can find, like, if you're doing simultaneous equations for the maths kids, 2 simultaneous equations where those lines meet is a single point. That's in 2D space. In 3D space, we need to have 3 lines to be able to triangulate, right? And so the idea is that if we had 3 ropes and we knew the length of all 3 ropes, we would be able to find where we were relative to the where those ropes were anchored. Yeah. Okay. The idea is if we have 3 satellites, we can find the center of those 3 points and we can know where we are. If you only had 2 ropes, there would be 2 locations where we could be. We could be here or here. The third rope is what, or the third satellite triangulates and tells us where we are. The reason we need a 4th satellite is because the information would be too inaccurate otherwise. So you need the 4th one to just for the matter of accuracy. Then, just because I got keen, I was going to write a little bit extra. The distances are corrected based on when the position was sent. So that's where, when they say where they are relative to Fiji, they also say when they sent the thing, and the GPS uses that to adjust the numbers. You probably don't need that, but if it was a 4-mark question, I'd want that. Okay. So, all right, what year? 24. One second. So I mentioned before my testing megathread, and so here I've got all the tests that we do. I don't have them in Google Classroom yet because I do this pretty early. So first of all, I've got this picture here, and one of my first memes is based on this specific question, 2014 paper, where let's just say it was not well received when this question was published. I haven't looked at really the marks recently. I will say that marks, nothing has been answered particularly well. 25 was answered well. Yeah, this is a hard test. Even then, that wasn't that well. 25C, yeah. Those last 2 questions. Yeah, it was a hard test. When I look at, the percentages, there's very few things that are up high. Anyway, moving on. This test, this was, I was teaching at this point in 2014, and I heard comments on ESNet about this question in particular, and I don't think I would have appreciated nearly as much as I do the difference between the IZOD and Sharpie test if it wasn't for IZOD. Now, also, this is probably the time where I can talk about my recent purchase of adventure it is. Okay, so when I was buying my laptop, I saw well, my daughter was looking for a High School Musical CD for a friend of hers, and we couldn't find that, but what we could find instead was Sharpay's Fabulous Adventure, and each DVD was $1. So we bought every single one of them. And then I had to take that receipt that had the laptop on it to try and claim it on tax, and the receipt has 8 Sharpay's Fabulous Adventures written on the receipt. So it looks like I'm a crazy person who just really likes Sharpay's Fabulous Adventure. And my daughter has been slowly leaving copies of Sharpay's Fabulous Adventure in her friend's car whenever they go somewhere. And every time she just gets a little bit more angry because she thinks it's the last one, but it never is, because there's always more Sharpay's Fabulous Adventure. Anyway, I've now just lost my Facebook picture. So I'm back. So this here is Sharpie, and Sharpie is a French dude, and he's lying down, and Sharpie was actually the person who came up with this test, I believe was a French person, and he lies down and he faces away. So just remember that it's a French person. I've got given him some a French thing on his shoes, and he's facing away. He's lying down, and he's facing away. And on the other hand, we've got this guy, General Zod. And General Zod, he fights Superman. And when he fights Superman, he doesn't lie down, he doesn't face away. The notch faces the hammer. So here we've got General Zod listening to his iPod. General Zod listening to his iPod, and he is facing the hammer. So this one here, what we can see here, this picture here, because it's lying down, the specimen is lying down, that is the Sharpie test. Now, I mean, I can find videos for these things. I think that 2000, material 2000, so if we do a Sharpie test. There we go. We've got a couple of them. So, you know what? I don't need to click on these. You have the internet. You guys can look at these tests. When we look at our grains, I know my typing always looks terrible. You got to remember I've got a microphone. So anyway, in this video, historic video, it really is great. This video, historic, maybe a bigger call, but in this test, this historic video, they show a test, and we'll have a look where we're quenching, and no, that's earlier. Here we go. Okay, so we've got a test. He's going to set up the test. Okay, so you can see the notch. I mean, there's probably 1,000 tests I could have got that are better than this one. See how there's the notch, and he's setting the notch up in between the machine so that just the notch is sticking out. And we've got a big hammer, and we're going to let it go. It was standing up, and the notch was facing the hammer, so that means it's an eyes-odd test. Now, what do you draw yourself? I mean, there we go. Okay, so that's the test. To do the calculation, what are we looking at? So work equals change in potential energy, PE minus PE1 minus PE2, which is 11 times 0.8 minus 11 times 10 times 0.23. So the change is 0.57, which is 63 joules. Boom. I rounded up. Now, the next thing is, this is how I drew the Sharpie test. I mean, now, I remember the scandal that was the Sharpie test. I don't know why this question was such a scandal. I'd only just started teaching, so for me it didn't seem particularly scandalous. But what have I got here? So 4 marks. I've 1 mark for identifying a test. Sharpie, boom, you get 1 mark. The second mark is, so I'm showing where the notch is relative to the hammer. Then, so notch and hammer. Then I've written its top view, so we're looking down on it. I guess I could have drawn it in like an isometric or pictorial representation. That would have been good. And then the 4th mark is, what does it test? It tests toughness. So you could have done, this one here is Sharpie. This one here is Zod. That thing there is supposed to be a hammer, right? It doesn't look like a hammer, but that's what it is. That's what it's showing as a hammer. And here's the hammer viewed from a top view. Yeah, they've even written top and front view. There you go. Good work. So we can keep going. And, we've got too many guys. We don't even need the paper at the moment. Okay. So, too many guys. Did I miss a page? Did I not scan? Yeah, I missed a page. Or the scanner didn't pick it up. Luckily for you, I wrote almost all of the notes. Okay, so we can, rather than writing out this formula, yeah, okay. I'll just quickly show you because the page is missing. And you can see it's clearly this, the scanner has not picked it up. But what we've got here is a boat. So first of all, I write M equals 1,300 kilograms, mg equals 13,000 newtons, and then I write too many guys. T equals mg, and then I write sine bracket sine theta plus or minus mu cos theta. Now, how I remember that is my friend Disco, he was going to a nightclub, was on a boat. He got there were too many guys. Then he hit his head on a sign because the boat, very low headspace. And then someone sneezed on him. and so he got mucus. Get it? Mucus on him. Now, just we've got to remember they've got to multiply both sides by mg, so that's why I wrote it in brackets. But you don't really need to do that. It's actually better if you write it expanded like this. And what we get is 4,000 and something, and we get 3,000 and something. Now, if we're preventing the thing from sliding, which I underlined, to prevent the thing from sliding, prevent the thing from slipping, so it means friction is our friend, right? Which means that friction is reducing the amount of tension that we need on the rope, right? The force on the rope. In that case, it's going to be like 700 newtons. Whereas when we want to actually start winching it up, we're going to need more force. Now, often in class, I will do some demonstration where I will like mime lifting up a boat, and I'll say, hey, I'm holding the boat and I can hold it together, but then we actually have to lift the boat up. I have to get another student up, and we both collectively mime lifting the boat up, which is probably funnier in actual reality than it is me describing it. Anyway, the point is that's the force. Then we have power equals force times velocity. When I first started teaching in 2014, I really struggled with this because it wasn't written on the formula sheets in 2014, right? It wasn't written on the formula sheets in 2014, right? Even though I can see it right there. Anyway, fight the power FV, fight the power FV, right? Like Flavor Flav. He's from Public Enemy. Anyway, so the force is this, right? We just calculated that. The velocity, they've even given it to us in meters per second. No dividing needed, thanks Ed Sheeran. And that gives us a number of watts. Then what we're going to say is efficiency equals pout over pin, right? P over power out divided by power in. Is that on the sheet? I don't think that is. No, you just need to know that. Okay, so when we rewrite it, we can say pin equals pout divided by 0.77. Now, a way to think about that is, if a machine is inefficient, it's not going to need less power, right? It's always going to need more power. The machine has to put out more power. If I need this amount of power to stop the thing from sliding, if I need 5,000 kilowatts to stop the thing from sliding, well, I'm going to need more power to pull it up. So there we go. Okay, I think we're at the last question. Came about suddenly. Okay, so here's the sample of what we're looking at, and then we're given this, the tow bar to start off with, and here's what I've drawn after that. So I'm going to bring this over, and am I going to rotate this? Yeah, I will. Okay. So, I mean, this is 8 marks. There's a lot of marks. So what are we looking for? These days, I don't think you'd get an 8-mark drawing question. You might, but I wouldn't think so. Drawings seem to have been less and less of a focus as years have gone on. So, make of that what we will. Okay, so first of all, there's marks for dimensioning. So 1 and 2. Now, if you look at the HSE answers, you'll see that it actually wanted to dimension the whole thing, which I don't know what a tongue is. What do I know what a tongue is? So I just thought it was this thing. And the reason why, I guess what they wanted you to do is they wanted you to calculate what was going on here. See, they told us that this drop was 40, and then I just used a set square. I didn't even use a set square, but I basically did a 30-degree angle. And they wanted you to do the total length. And I'm like, where would that even go? It wouldn't barely fit in the paper. You have to write the dimension right where it says end of paper. So anyway, I wrote that. I think they'd still give me my mark. As long as I've drawn the arrows, my lines aren't touching. I'm using a thin dark line. Okay, the next thing is that the next thing I did is, after I drew this general shape, right? The next thing I did is I drew these 2 holes. And I actually used a ruler for this. I didn't just eyeball it like I normally would. And so I put my center lines in. And once I did my center lines, I then did... it says here that this is an M16 threaded hole. Now, with holes, right, when we have threaded holes, the major diameter is the outside diameter, and the minor diameter is the inside diameter. So that's just worth noting that... that the dark line is the inside line and the light line is the outside line, and that when we hatch into that, because it's empty, there's nothing there, we have to hatch into there. Now, I would make a mark for that. If it was me, I would have a mark for that. Now, I don't have many spacings, but I have enough that I can demonstrate. I always like to do my hatching really wide because I think it just saves a whole lot of time. but you can see that I've just done enough to show that I have hatched in the thing to show that it's threaded and that there's nothing in the thread. Then you have to include this line here because theoretically you can see, well, not theoretically, you should be able to see that line on the outside, and I don't know why they didn't include that. Here, what I've done is I've just drawn my thread, and now this time 16 is the outside diameter, and my inside diameter is 18 is the outside diameter, 16 is the inside diameter, because they've told us the pitch, I think. Oh no, I thought they told us the pitch. Yeah, okay. So because they haven't told us the pitch, oh no, they have. They did tell us. They told us here. I was like, where did I just make that up? No, because it's a fine thread, so they've told us that the pitch is 2. So that means the inside, the minor diameter is 16 minus 2, 18 minus 2 is 16. Then I have drawn the washer. The washer dimensions were given in this case. Yep. And then I've drawn the, I didn't draw the spring. Yeah, so shoot me. I drew now this is a nut. So remember, head at 7, nut at 8. So this rectangle is going to be 1.8 times, I wrote 1.8 times 16 and not 1.8 times 18. Huh. Yeah, so my dimensions are actually wrong. That's why it looks a little bit shallow. Yeah, oh well, exam conditions. I think I'd be okay. I actually did write 1.8 times and 0.8 times. I don't know if I would gain a mark or lose a mark because of that, because I've explicitly said that I'm wrong, but at least I showed some knowledge. Anyway, then I've got the sleeve. The sleeve needs to be hatched differently. And then we've got dimensions. So I've got 1, 2 dimensions, 1, 2 dimensions, 2 different kinds of hatching, that thing there as well, maybe. So 1, 2, 3, 4, 5, it's 8 marks. I mean, there's going to be other things we're looking for. The general shape is definitely 1. The fact that we show the termination of the thread here, that's another one. So general shape 1. I would also mark for the center lines. I know I'm a weirdo there. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, maybe 9. Yeah, so I mean, it can't have 9, but you get the rough idea. So 1 for the general shape and knowing what's going on. 1, yeah, you wouldn't get the center lines. There you go. That's the 9th one. 1 for showing the empty thread here, or getting your threads right there and there, getting the bottom of the thread, showing the hatching, different kind of hatching there, the nut there, and 2 different kinds of dimension. That's how I would mark that. Okay, we'll just quickly show the HSC answer because it's a good answer. Okay, so you can see that their hatching is much tighter than mine, but you know, that just means you have to do more work. So I don't like to do more work. You can notice that they dimension the diameter differently to me. They did their dimension here differently. They also showed the spring washer, and look, you don't even notice that that's wrong. So there you go. Hopefully that was of some benefit.